Let's start with this problem. This is related to the Heisenberg equation of motion, what we have just learned. Now we have two observables A and B. We need to show that time derivative of the product of the two observables A, B looks like this. Now as A, B, they are both observables, so we can associate operators with these observables. So if we want to prove this relation, and if we prove that ddt of A operator, B operator, that is the product of A and B operators, equal to A operator time derivative of B operator plus time derivative of A operator multiplied by time derivative of just the B operator, that will do also. So for observable A, the operator is A operator, A hat. Heisenberg equation of motion looks like this. And for B operator, it looks like ddt of B operator equal to BH plus del T of B. Now we are considering that A and B both have explicit dependence on time. Now according to the Heisenberg equation of motion, the product of the two operators, A operator, B operator, and their time derivative looks like the product of the two operators AB and the commutation relation of this AB and the Hamiltonian and the time derivative of the product AB, A operator, B operator. So here we have just using the normal commutation relation rules. So we can write from this term, we can write these two terms, and from this term we can write these two terms. I'm sorry, this is a little bit clumsy and dirty, it looks dirty, but it's quite obvious and simple, so we can derive it also on our own. And now if we take this A operator common, we are left with the commutation relation of B and Hamiltonian and the time derivative of this B operator. Plus we have the commutation relation of the Hamiltonian itself and the A operator. And the time derivative of the A operator and B operator is there outside the parenthesis. But instead of this term, we can easily use the Heisenberg equation of motion for the B operator. Similarly, we can also use the Heisenberg equation of motion for the A operator. And now we have proved this. What do you want? Let's discuss a few problems today. First, we'd like to discuss this problem. It is said that an operator which commutes with Jx and Jy, we need to show that it must also commute with Jz. Now we have already gone through this what is Jx and what is Jy, what is Jz, etc. We know that in quantum mechanics, these individual components of momentum, they do not commute with each other. Now we know that J plus, we define this J plus operator in my previous angular momentum operator series. So we have already defined that this J plus equal to Jx plus Ijy. As that operator, let's call the operator O, and as this O commutes with Jx and Jy, so it must commute with J plus also. We know that the commutation relation of Jz and J plus looks like this. So Jz J plus can be written like Jz J plus minus J plus Jz equal to H cross J plus. So here we have written the expression of J plus in terms of J plus itself and Jz. H cross is constant. And as we have this condition that this operator O must commute with J plus, so we can write this must be equal to 0. This means that this operator must commute with this term. It also commutes with this term. And these commutation relations are possible if and only if this O operator commutes with Jz. We now have this problem. We need to write down two 2 by 2 matrices which are simultaneously Hermitian and unitary. We need to also calculate their summation is Hermitian, and we are asked that is the summation is also unitary or not. So for the time being, we are taking Pauli spin matrices. Pauli spin matrices is also discussed before. Now we have this sigma z and sigma x spin matrices. We knew that sigma z is 1 0 0 minus 1 and sigma x is 0 1 1 0. So if we need to show that the sigma z is Hermitian, we need to show that sigma z dagger equal to sigma z, which I have shown already. Because making sigma z dagger is basically making this row into column and this row into column, and so this is what we get as a sigma z. So this is this sigma z is Hermitian. If it is unitary, then we need to show that sigma z dagger and sigma z, when they multiply with each other, they gives us an identity matrix, and which we have calculated, which we have shown. So I have also shown that sigma z is unitary. Similarly, sigma x is Hermitian because the sigma x dagger is 0 1 1 0, which is the original sigma x matrix. Now we need to calculate that whether sigma x dagger sigma x equal to 1 or not. Yes, this is 1 because sigma x dagger is this one, sigma x is this one. So when we multiply this, we get this unitary operator. So we have shown that sigma x is a unitary operator. Now these are two very important property of these two spin matrices. We came to know that this sigma x, sigma z, these are unitary and Hermitian. Now I would like to check whether the summation is Hermitian and unitary too. So this is their summation. Again we are making sigma x plus sigma z dagger, which is sigma x plus sigma z. So their summation is also Hermitian. But if we see that their summation is unitary or not, what we have found is when you multiply this, their summation, I mean this one with itself, then we found that this is not unitary. So their summation is Hermitian but not unitary. Let's discuss a problem involving angular momentum. Now angular momentum is extremely important in both classical and quantum mechanics. We have three fundamental properties of motion. One is angular momentum, second is linear momentum, third is energy. So in atomic and molecular physics, angular momentum plays a very fundamental and very important role. Here we are going to exploit symmetry of rotation, that is rotational symmetry. The problem is a certain state psi is an eigenstate of L square and Lz, where L square and Lz on this state psi satisfy these relations. Now for state psi, we need to calculate the expectation value of Lx operator and expectation value of Lx squared. Excuse me, Lx squared. Now we know that all these things, this Lx, Ly, Lz, L square, they correspond to real physical variables. So they are Hermitian operators. So Lz is also an Hermitian operator, and that satisfy these relations. And if LZ is an Hermitian operator, we can write this without any objection. Now we need to find out the expectation value of Lx. Expectation value of Lx is nothing but the Lx operator sandwiched between the two states psi and this psi. This kth psi and this bra psi is there. And we know from our angular momentum commutation relation video, this cyclic permutation relation is always obeyed among all these angular momentum operators. I am using this one, that IH cross JX equal to the commutation relation of JY JZ. So here in place of Lx, I have written the commutation relation of Ly Lz. And it looks like Ly Lz minus Lz Ly 1 by IH cross, that is a constant. I can easily take out from the expectation value itself. So here Lz if Lz operates on psi, that gives me MH cross. This Lz operating on this bra psi gives MH cross. So MH cross by IH cross, that is outside the parenthesis, we are left with this. So we have 0. So on this state psi, the expectation value of Lx equal to 0, and the physical significance of it is this is eigenstate of Lz, because measuring Lz on psi gives me MH cross. So measuring Lx on this psi must give 0, and we have obtained it mathematically also. Now we are considering the symmetry of the problem, the rotational symmetry, because angular momentum correspond to a rotation. And symmetry of the problem tells me that Lx square must be equal to Lxy square. The two expectation values should be same. And this is also from the symmetry of the operation. And in place of Lx square plus Ly square, we can write L square minus Lz square. So here in place of Lx square, if we apply this, and if we use these relations, this one and this one, we have obtained this. So this is the expectation value of Lx square on psi.